So hello everyone, welcome to this final video under module 3. So till now we have covered all the concepts starting from the introduction part of the real-time operating system and general purpose operating system. Under that we have discussed different kernels, that is monolithic kernel and microkernels. After that we have discussed with the scheduling techniques, okay, where we have seen different kinds of scheduling. Under that we have seen first is preemptive scheduling, then we have round robin scheduling and priority based scheduling. After that we have discussed with task communication and task synchronization. Under that we have seen one condition, that is deadlock. Okay, so these are the things covered in this module. Okay, so now we have one final concept left related to the integration and testing of embedded hardware and software. Okay, how the integration and testing is done in any embedded system between the hardware and software, they have mentioned it here. So integration of hardware and software or the firmware deals with the embedding of firmware into the target hardware board. It is a process of embedding intelligence to the product. The embedded processors or controllers used in the target board may or may not have built-in code memory. If the processor or controller does not support or built-in code memory or the size of the firmware is exceeding the memory size supported by the target processor or controller, an external dedicated EEPROM, that is erasable programmable read-only memory or flash memory chip, is used for holding the firmware. That is, if one hardware would be there and one software code would be dumped into that, if that hardware does not has the capacity to hold that software or the firmware code, what it does is it adds some extra memory, that is called as EEPROM or flash memory chip, under that hardware in order to hold that remaining code. Okay, so that is called as integration part. So that chip is interfaced to the processor or the controller, that is the hardware part. A variety of techniques are used for embedding the firmware into the target board. The commonly used firmware embedded techniques are mentioned here. Okay, so these are the five techniques here. So first one is out of circuit programming. Then we have in system programming (ISP). Then we have in application programming, that is IAP. Then we have use of factory program chip, and we have firmware loading for operating system devices. In these five techniques, we are going to see with only first three techniques, that is out of circuit, in system, and in application programming. Okay, because in the syllabus point of view, the last two techniques are not so important. So let us discuss first with the out of circuit programming. Okay, out of circuit programming is performed outside the target board. Okay, that is it is given outside the some part of the inside the embedded system only, it is given separately. Okay, it is performed outside the target board. The processor or memory chip into which the firmware needs to be embedded is taken out of the target board, and it is programmed with the help of the programming device. Okay, so the firmware which needs to be added to the circuit, and that part of the circuit is taken outside the target board, and in that the code is getting interfaced. Okay, the programming device is a dedicated unit which contains the necessary hardware circuit to generate the programming signals. It contains a ZIF socket with locking pin to hold the device to be programmed. The device will be under the control of a utility program running on a PC. Okay. The commands to control the programmer are set from the utility program to the programmer through the interface as shown in the figure. So you see here we have one PC COM, that is the USB port, and this is the device programmer which is given separately. Okay, so and this is the RS-232 USB cable, and this is the DB9 connector which is used to connect between these two ports. Okay, so this is the programmer part. Okay, this is the PC, and this is the separate device which is used for interfacing between the embedded system. Okay, so this is one example of the out of circuit programming. So these are the sequence of operations involved in the out of circuit programming. First, that is connect the programming device to the specified port, then power up the device, execute the programming utility on the PC, unlock the zip socket by turning the lock pin, then insert the device to be programmed into the open socket, then lock the zip socket, select the device name from the list of the supported devices, then load the hex file, that is the which is to be embedded into the device. Program the device by program option of the utility program. Wait till the completion of programming operation. Ensure that the programming is successful by checking the LED status. That is, if you want to check that the program is successful or the interfacing is proper, then we should be adding one simple LED so that if it blinks, the program is successful. Then unlock the zip socket and take the device out of the program. Okay, so these are the steps of operation for the out of circuit program. So this was one, and we have some of the drawbacks here. So one is high development time, and then we have it facilitates programming for only one chip. Then once the product is deployed in the market and in a production environment, it is very difficult to upgrade. Okay, so these are the major drawbacks. So now the next type is in system program. Okay, so this is very important. In system programming, that is also called as ISP. So in this in system programming, it is done within the system. Okay, that is whatever programming part should be done in the out of circuit. What we have seen, it is done outside the system. Whereas in system programming, where whatever changes or any adaptations to be done, which it is done within the system, which means that the firmware or the software is embedded into the target device without removing it from the target board. Okay, whereas in the out of circuit programming, it's the device should be removed out of the target board, whereas in system programming, the target device is not removed from the target board, it should be there inside the target board itself. Okay, it is the most flexible and easy way of firmware embedding. The only prerequisite is that the target device must have the ISP support. Okay, the communication system between the target device and the ISP utility will be in the serial format. Okay, that is the communication will be taking place in the serial format. That is one after the other. It would be taking place in a sequential order. The serial protocols used for ISP may be Joint Test Action Group, that is JTAG, or Serial Peripheral Interface. So this part we are using mostly for the in system programming, that is the Serial Peripheral Interface, because we are doing it in a serial format. Okay, so let us see this in system programming with SPI protocol. So devices with SPI in the in system programming support contains a built-in SPI interface and the on chip, that is EEPROM or flash memory, and it is programmed through the interface. Okay, the primary IO lines involved in this SPI in system programming are listed below. That is, first we have master out slave in, then we have master in slave out. So these are the bus lines. Then we have system clock, reset of target device, and the ground of target device. You see here master and slave block under peripheral serial peripheral interface. So under master we have serial clock, master out slave in, master in slave out, and serial system. Okay, that is the ground. So you see here three slaves for all the connections, interconnections are made. Okay, so master out slave in is given, and master in slave out is from one slave of the master out slave in is given to the interfacing part, and the ground is connected to all the three slaves. Okay, so this is the SPI protocol which is used for in system programming. Okay, so this was about in-system programming. So some other explanations are and all, if you want, it is there in this, which about what the PC would be taking place in this thing. Everything explanation is there. So this PDF would be available in the description. Go and access it and read this. Okay. So without wasting further time, let us get to the next part, that is in application programming. Okay. Under this in application programming, it is a technique used by the firmware running on the target device for modifying a selected portion of the code memory. Okay, so this is same as the in system device. It is taking place inside the target device only. The system, that is the target components, are not taken out of the target device. But there is one slight change, that is, if you want to make any changes or alterations in the program code or the firmware code, a selected portion is taken from that code software, and that portion is taking and put that portion would be getting modified. Okay, so that is called as in application programming. It is not a technique for the first time embedding of user written firmware. It modifies the program code memory under the control of the embedded application. Updating the calibration data, lookup tables, etc., which are stored in code memory, are some of the typical examples of the IAP. Okay, so the boot ROM resident API instructions, which perform various functions such as programming, erasing, and reading the flash memory during the ISP code, ISP mode, are made available to the end user written firmware for the IAP. The boot RAM, this is one typical example which you will be taking for the in-application programming. It is shadowed with the user code memory and in its address range. This shadowing is controlled by the status bit. When the status bit is set, the accesses in the internal code memory in this address range will be from the boot RAM. When cleared, the access will be from the user's code memory. Hence, the user should set the status bit prior to calling the common entry point for the IAP operations. Okay. So, uses of this factory program chip under this application in application programming is mentioned here. Okay, and this was about a in application programming. Okay, so uses of factory program chip and firmware loading, as I've told you, that's not required. So that's why I'll stop at this point. And for the different approaches used for the integration and testing of embedded hardware and software. Okay, so these are the five approaches, and out of that, three approaches I've discussed. So go through it. Okay, so we have one more important concept which is very important. So this was there in the model paper as well. That is embedded system development environment. Okay, so this one question they had asked in the model paper, so that's why I thought of doing this. So the development environment consists of a development computer, that is PC or host, which acts as the heart of the development environment. Then it consists of integrated development environment, that is IDE tool for embedded firmware development and debugging, electronic design automation, that is EDA tool for embedded hardware design, and emulator hardware for debugging the target board, signal sources like function generator for simulating the inputs to the target board and the target hardware. So these are the things which is present in the embedded system development environment. So you see here, you have the figure here. Here we have the development host, that is a PC. Then this is the PCB fabrication files which is there inside the CPU. So this is the integrated development environment tool under it is present inside this CPU, that is the IDE tools. Okay. Then we have the emulator interface, which is used to do the interfacing between the emulator and the PC here. Then we have the socket which is used for the connections. Then you have here one target board. The target board is used for the signal sourcing, that is a function generator, in order to check the inputs simulation, so in order to simulate the inputs which is directly to the integrated development. Okay, then we have the hardware debugger interface, that is the multimeter. Then we have the logic analyzer. In order to check the outputs, we have an analyzer where the signal would be signal transfer would be taking place, and we could be viewing the output change in this logic monitor. Okay, so this is the complete interfacing part of the embedded system design environment. So this is the figure, guys, you please note it down. Okay, so this was about the embedded system development environment. So I thought of doing this because this is there in the model paper, that's why. So that's all, guys. So this is the completion of module 3. I've covered the most of the concepts by referring these notes from the VTU sync.in. So this is a standard website of VTU where you would be getting all kinds of notes for all the subjects of 6th Sem. A huge shout out to them because this notes was very essential. So that's why I thought to do it for module 3. All the concepts are explained beautifully. So this I'm going to put it in the description. Go and access it and please study it. Okay, each and every concept is explained beautifully here with the necessary diagrams. So that's all for the video, guys. I've completed module 3. Two more modules are left, module 4 and 5. Those are completely based on ARM processors. Okay, ARM fundamentals, that is ARM, module 4 and 5, where in module 4 it is completely about the introduction part of the ARM processor, and module 5 it is completely based on the instruction sets used in the ARM processor. Okay, so let us discuss that in the upcoming videos. So that's all for the video, guys. Thank you.